Hi guys, welcome to section 2.6. Today's lesson is a little bit longer and it's really an important concept in this chapter, probably one of the most important concepts in this chapter. That's why I made you guys do an entire project on this. So we're finally at our piecewise function. So you might have to listen to this lecture a couple times just to get it, because like I said, it will be very confusing for you at the beginning. So let's first start out with some warm-up problems. Please note for number 2 before we correct it, that you need to write your answer in point slope form and slope intercept form. So give me both equations and we'll correct them in a second. So pause and then return back. All right, for number 1 is a review of chapter 1. So it's a compound inequality. So your answer should be negative infinity to negative 1 with a bracket because it's an OR problem. So you needed to have the graph there and most importantly, your interval notation. Then for number 2, your point slope form, the one in red, that you can have either one of those equations. It just doesn't matter which point you use. And then the purple is your slope intercept form. And I did this to show you guys, again, some of you guys are probably annoyed that I keep on saying it's so easy. It's way easier with point and slope, and it is. Here's the work to show you guys how easy it is. The slope you guys have to find for anything. So the blue for finding the slope is what you have to do for either problem. But point slope, there's literally no work because you have a point, you have a slope, and you just write it down. Those of you guys who are still stuck, and you guys will be until like the death of you, are still stuck in your slope intercept form, look how much more work you have and look how much more work you can get wrong because there's a lot of fractions going on. So when we are grading the test as teachers, we are always a little bit more lenient on giving points and like little mistakes and errors on people who stick with point slope form because that's the way we want it. But if you get something wrong in slope intercept form, like we are all or nothing, like you get it wrong. So if you accidentally put negative 15 thirds and on the slope intercept form instead of negative 13 thirds, it's all off. As opposed to point slope, we're a little bit more lenient because we want you to use that format. So again, please just use what I tell you is easiest because I know better and it is easiest. All right, number 3, it doesn't specify which type of equation you want, so you could use either one. As we know what one I want you guys to do, which is that first one. But if you so happen to want to play around with fractions, just know that you'd have to solve for B and get the 27/5 part if you wanted it in slope intercept form. All right, so now let's start our piecewise function. So we're going to first start out with evaluating them. And you might be like, what is a piecewise function? A piecewise function, again, in math, we're not creative. Piecewise meaning pieces of a function. That's all it is. It's just like little parts of graphs all smashed together. That's exactly where I made the concept of your project in. It's just pieces of graphs all put together to make like a smashed graph of some sort. So this is how you're going to notice how piecewise functions are written. So you're going to have like this big curly bracket. And then h of x, we also call it like y. So you might like it's y equals. And what this means is that it just y equals these 3 equations. So it's y equals 3. This is a y equals this, which is a parabola. And y equals 1/4 x plus 2, which is just a line that we've learned how to graph in this chapter. Okay, so it's just 3 graphs on one graph. And then what these little parts mean, if this is like the boundary they're on. So it's going to be, for example, for number 1, it's going to be y equals 3 for numbers that are less than or equal to -2. And then the second one is this parabola equation only in between numbers -2 and +2. Same thing with this one. So this is this line for numbers that are greater than 2. So this tells you like where on the graph that these graphs will appear. But we're going to learn how to graph that. That's like our main concept today. But first off, we're starting off with just evaluating. So it says find h of 0, find h of -2, and h of 4 because this is an h of x function. Okay, so what do these numbers mean? It means a domain. Okay, remember X is our domain. So we're looking at these. These are your domains. Okay, so all you have to do is find where each individual one is located. So for example, for h of 0, you find which one of the equations, I'm going to call this like 1, 2, and 3. So which one of the equations is 0 in that inequality? So look at, for example, the first one. Is 0 less than or equal to -2? No, so it's not defined in that one. So it's not that one. Then you go to the next one. Is -2, is it 0 in between these two numbers? Yes. So it is housed basically in this number 2 equation. So all you have to do now is go to this equation and we're going to plug in 0. So we just do h of 0 and we just plug in 0 to that equation. Use our PEMDAS accordingly. So it's 1 squared minus 2. So my answer for h of 0 is -1. All right. Now we move on to the next one. H of -2. So you find again, where is -2 in your domains? Okay, where does -2 fit? -2 fits in the first one because -2 is less than or equal to -2. Okay, so then you plug it into that equation. That equation is just y equals 3. So there's nothing to actually plug it into. It's just any number that's going to be less than -2, you're just going to write 3. So nothing to solve there. You like those ones. So just 3. And then the last one is h of 4. Okay, so again, you look at which domain out of 1, 2, and 3, where does 4 fit into? And it only is going to ever fit into 1. It's not going to fit into like multiple. It's only going to fit into 1 because this is a function, remember, so you only have one domain. Okay, so 4 fits into the third one because 4 is greater than 2. Okay, so it's in that domain. So then you plug it into that function. Okay, so you do 1/4, and we're plugging in 4 plus 2. 1/4 of 4 is 1, plus 2 is 3. So the answer there is 3. Okay, so that's how you do and define these problems. This is setting you guys up for when we're going to learn how to graph. So again, you look at where each of these domains fit into your domains here, and then you just plug them into the specified equation. So this should be very easy for right now. Okay, number 2, same idea. Okay, so let's find f of -5. Okay, we're going to find where is -5 defined on these 3 inequalities. Okay, it's only going to be attached to one of them. So -5 is in the first one because -5 is less than -2. So you just plug it into the equation, and the equation here, there's nothing to plug in. So your answer is just going to be -2. Okay, next one, f of 0. So let's find out where 0 belongs. 0 belongs in this inequality because it's in between -2 and 1. So now you plug in 0 to that equation. So we're going to plug in 0 for x. So it's -1 squared plus 1. So -1 plus 1 is 0. So the answer for f of 0 is 0. And then lastly, you get f of 2. So where does 2 belong? 2 belongs to the last one because it's greater than 1. And what I don't want you guys to think is that, for example, like each of these belong to a certain one and they can't overlap. They can definitely overlap. I'm just making these like nice, easy problems where there's one number per equation, but I could definitely have said, and this is what you'll see like on Alex or your test, I definitely could have said, for example, this is f of -6. And then -6 would have fit back into that first equation we already used, and that would have been fine. So it's totally fine to reuse equations. So don't just assume that. All right, so f of 2, again, belongs in the last one. So we're going to plug it into here. So it's going to be 1/4 of 2. So 1/2 minus 1, let's make common denominators of 2. So 1/2 minus 2 over 2. So your answer is -1/2. Again, you're going to forget this probably tomorrow or something, so please revisit this section if you have questions. But now we're going to get into domain and range before we actually start graphing. And per all our notes, by the way, because now we're going to start getting into actual content where our lectures are longer, please pause and take a break whenever you guys need to, especially in something like this where it's going to be really complicated. Take a break if you need to. There's no need to power through all this in one sitting. All right, domain and range is kind of similar to our increasing and decreasing intervals we visited. So make sure you guys are just using and paying attention to closed and open circles for parentheses and brackets. And I know you guys know that domain is the X and range is the Y. All right, so domain and range. So for domain's the X. So for example, on the X axis, it starts at -3 all the way to 2 is where it stops. So you always go left to right for domain. So it's going to start at -3 with a bracket because of that solid circle here. And then it stops at 2, but it has a open circle, so we have a parentheses there. So from -3 to 2 are the numbers on which this graph is defined. And then for range, we go bottom to top. And yes, it matters if we're going left to right and bottom to top. You have to be going in numerical order. So for example, this would never be 2 to -3. That's not in numerical order like how a number line works. It always has to be numerical. So bottom to top, the smallest number on the range is -4. And -4 again is an open circle. So we're going to keep it with parentheses. And then up here, there's no circle. So you're like, well, is it open or closed? If it's touching, that means it's closed, okay? A closed circle, again, means it's defined at that point. So it actually hits 5, so it's defined there, so you would use a bracket. All right, same idea on number 2. So domain is always left to right, so the most left point is here, and it goes all the way to the most right point over here. So it starts at -3 because of the closed circle, and then ends up at 2 within parentheses or open circle. And then we have to go bottom to top for our range. I think that's the one you guys usually miss. Range, you guys are pretty good at left to right, but domain, you're really good at left to right. The range, you guys forget to go bottom to top. So from the most bottom point is -4, and that has a closed circle, so we're going to use a bracket. And then it goes all the way up to 5, and there's no circle there, but since it hits 5, we need to assume it is defined there, so we will put a bracket. Number 3, domain and range, so -5 to 5. And then the original -5 is a bracket because of the closed circle, goes to 5 with an open circle. And then bottom to top, -3 all the way up to 5 with 1 parentheses and 1 bracket. All right, then we get into 1. So these are all just had like 1 line. Now we're getting into some that have like 2 lines. This is kind of like what a piecewise function looks like anyways. So, because there's like pieces of functions going on. So we're going to have actually 2 domains as you can see here. So you go -2 to 0, and then there's a break, and you guys need to account for that break, and we're going to use a union like we learned in chapter 1. And then it starts back up at 2 to 5. Okay, so we need to account for that and write the intervals accordingly. So again, it starts on the leftmost point at -2 with a bracket, and then it stops at 0 with a parentheses. And then to account for there's like a little break, you put a union, and then we start back up at 2, and we end with 5 bracket. So we're not, just because there's 2 lines doesn't necessarily we're going to have 2 domains and 2 ranges. So if you see here, this line is kind of enveloped into this line if we're looking at range, because the lowest point is -4, and it actually hits all the points all the way up to 1. So there's actually no jump. There was only a jump side to side. There wasn't a jump going top to bottom. So just because there's 2, you can have 2 domain and ranges. It's just not necessarily. You have to like approach each problem differently. So it's going to be dependent on the problem. So in this case, there's only 1 interval for your range. And that interval goes from -4 on the bottom, and it goes all the way up to +1, and there's no gaps or breaks there. So understanding that we just learned that, try number 5 all by yourself. All right, so this one was 2 lines and it actually had 2 domains and 2 ranges. So as you can see, jumping from left to right, there was a jump and a gap, as well as going from bottom to top, there was also another gap. So this one did have 2. So again, it's not just always going to be just because there's 2 domain and ranges. You just have to approach each problem. All right, so now for the big part of the day, graphing piecewise functions. So there are 2 types in ALEKS and 2 types we're going to learn about. The first type is the one we're going to do first. It's supposed to be the easier one, but then I feel like as you guys start learning this, you guys tend to think this one's the harder one. So we'll revisit that at another time. So again, a piecewise function are just pieces of functions. And the key word being here, function, remember when we learned about functions, it needs to pass the vertical line test, meaning these graphs are not going to overlap at all. So you're not going to be getting things that overlap like this. You're going to be having like part of a function and then like another part of a function and then something else. Okay, they don't overlap. They would always pass the vertical line test. Okay, so that's something to keep in mind because that's where most people make mistakes, is that they ignore the fact that these are functions at the end of the day. Okay, so again, I wrote that here. They will never overlap, 1 graph per area. All right, so I'll explain all this neighborhood and fence vocab I kind of use with you guys. All right, so again, here are piecewise functions, and this is how they're always written. So you always have like your little big bracket. And then f of x, just think about it as y equals, just to make your life easier. So it's y equals x, it's y equals 1, it's y equals 1. So it's just these 3 graphs. You guys know how to graph these graphs. They're things you guys have been doing in Algebra 1. Now we're just breaking them up into little pieces depending on their x values. That's all we're doing here. So do not overcomplicate it. All right, so first of all, we're going to draw our neighborhoods because each of these are like, we're going to think of them as like communities that belong in these neighborhoods. So if you look at your X numbers, so look at over here, the 2 numbers we're basically dealing with are -2 and +2. So what I want you to do is draw your neighborhoods, meaning put a vertical line down at -2 and +2. So now each of these lines, y equals 1, y equals x, and y equals 1, is going to belong in each of these neighborhoods, and they're not going to overlap. So one of them belongs in each of those little blocks. That's why we block it off first. Okay, so let's approach the first one together. So the first one is y equals 1. The graph of y equals 1, like I said, it's going to come up a lot when we learned about graphing. Y equals 1 is just the horizontal line at 1. Okay, however, it's y equals 1 only at x is less than or equal to -2. So where is that on our graph? It's this neighborhood because it's all the numbers less than -2. So we're only going to be graphing in that area, and we're going to be graphing the line y equals 1. The line y equals 1 is this line. Typically, like we know, it's all the way through, but like I said, we're doing piecewise functions, meaning we're only graphing part of the graph. Okay, the next big part is that you're going to need to have open and closed circles on these lines and on their boundary points, which we call fences. So those pink highlights are our boundary lines. We're going to call like your neighborhood fence. So the most important part here is that this was like a closed circle if we were graphing it like in chapter 1. So at this point, we're going to put a closed circle, and that's going to matter when we start getting into these harder problems. All right, so that's just the first graph and first neighborhood. Now let's do the second graph. Okay, so again, it's just a y equals x line. If we were in Algebra 1 and your problem was graph y equals x, I think you guys know how to do that. Okay, however, it's just in this boundary line. So where is -2 to 2 in your neighborhood? It's this boundary. And by the way, just because it's the second line doesn't mean it's just the second boundary. You just have to pay very close attention. So we're in that second boundary because those are the -2 to 2 lines. Now we're just going to graph y equals x in between those two lines. So what I'm going to do is I'm actually going to use these points just to make my life easy. So I'm going to plug in -2 and 2 into y equals x. And obviously you're going to get -2 and 2. So plot those points. And connect your dots. You might be thinking, well, why did she make one open and why did she make one closed? Again, you have to pay very close attention to our signs here. At the -2 one, we had a less than symbol, which equates for an open circle. And then for our +2 one, we had a less than or equal to symbol, which equates a solid circle. So that's how I got to know which ones were open and which ones were closed. Again, lots to think about per problem. And then the last one is the same thing as the first one. It's still y equals 1, so it's still a horizontal line at 1. However, we're just in this neighborhood now. So we're in the x is greater than 2 neighborhood. The x is greater than 2 neighborhood is this one. But it's the same exact line we first drew. So it's still this line. It's just in the other neighborhood. And then what circle are we going to have? We're going to have an open circle at 2. And there's your graph. So a couple things to note and why I draw these neighborhoods. Your final answer doesn't have the boundary lines in them. So like if you were drawing them on Alex to help yourself out, please erase them because you'll be marked wrong. If you're giving me like a pencil and paper test, you can leave them, I don't care. But technically it's wrong, you don't need them. But the reason I do keep them there is that only one person can sit on the fence, which is something with my note here. So, meaning you're only going to have one open and one closed circle per fence. So as you can see, there's one open and one closed. Here there's one open and one closed. Again, because this is a function and it needs to pass the vertical line test. We can't have two closed circles or it wouldn't be a function. So That's just something I check real quick before I erase my boundary lines. And then that would be my final answer. All right, so let's try number 2 together. These ones are actually, once you get to know them, pretty fun. So we didn't have a graph here because, as you can see, there's like a lot of decimals going on, so I just wanted to freehand this one and sketch it out. So start drawing that. We're going to go by increments of 0.5 on the x, because as you can see, all the x ones are by 0.5. But all the y's, which are here, are just by whole numbers, so we're fine. Actually, we'll go by 0.5 on those two, so we don't confuse each other. All right, so everything's by 0.5. And just so my notes are nice when I come and check them, when I'm studying for my test, I'm just going to label. Just one axis, so I kind of know what was going on. All right, so again, however many lines or equations you have is how many boundaries or neighborhoods you should have. So the first thing we should be doing is deciding, where are my neighborhoods? And your neighborhoods are all these numbers here. So wherever you see one of these numbers, draw a vertical line through it. So for the first one, it says -2.5. So we're going to put a line at -2.5. which is right here. Okay, we're going to also put a line at -1.5, which is right here. Okay, and then you keep on doing that. So again, you have -1.5. We already have a line there, so we don't need it. And then at -0.5, -0.5 is here. And then we already have -0.5, so we're going to +0.5. And then we keep on going until we've marked all boundaries. So again, we have 5 lines here, and I have 1, 2, 3, 4, 5 neighborhoods. So it all makes sense. So each of these graphs are going to go in a particular neighborhood, depending on the domain of the graph. And again, just because, I'm just going to reiterate this, just because this is the first line doesn't mean it's going to go in the first boundary. It's not always going to work out like that. It's going to work out like that a lot, but it's not going to always do that. So do not get too comfortable there, especially on a test. Hint, hint, we probably won't put it in order. All right, so let's go through each one. So this is a y equals -2. Again, just a y equals number is just a horizontal line. So this is a horizontal line at -2. So if we were just drawing like a normal line, that's what a y equals -2 is. However, we know it's only defined on -2.5 to -1.5, which is this boundary. So all we're going to do is just cut that line so it just fits in that boundary. So it's just going to be here. Okay, we need our open and closed circles on our fences, so pay attention. The left circle is going to be open, the right circle is going to be closed. So open, closed. All right, first neighborhood done. Second neighborhood, y equals -1. Again, these are really easy graphs because they're just horizontal lines. So now we're going to be at -1. So since we're going by 0.5, it would be over here. So this is the graph y equals -1. However, we're only in this neighborhood, the -1/2 to -1/2, which is this second neighborhood. So we're just going to draw that horizontal line in the second neighborhood, which is here, paying attention to open and closed circles. So we have an open, then a closed. and that's your second neighborhood. Third one is y equals 0, so a horizontal line at 0 in this third region because it's negative half to half. So another horizontal line. And again, it's an open and then another open. So they're actually both open circles on this one, so pay attention. Next one is y equals 1. So a horizontal line at positive 1 in between these two numbers, which happens to just be, now everything's going in order on this one. So you got lucky. So it's in this region. And now we're just going to draw a horizontal line at 1. And this one is a closed circle on the left, open circle on the right. And then losing colors, we'll do pink. So y equals 2 on that last region. As you can see, it's going to be horizontal at 2, and it's going to be closed, then open. Okay, so a couple things you should always check before you erase your boundary lines. Always making sure nothing's overlapping. So this does pass, for example, the vertical line test. Like if you wanted to, again, have your vertical line test and you're dragging this across, it doesn't hit two things at once, so you are good for that. And then you can see each boundary line has an open and closed circle on it. So there's never like two solid circles on it. So we're good to go, meaning this passes a function. So you just erase these, and that would be your final graph, just little pieces of lines that never overlap. When I say never overlap, again, I'm meaning something like this blue line would never extend over here because it wouldn't pass the vertical line test. They just stay in their own little lanes. All right, so that is number 2. You guys are actually going to do number 3 by yourself, but hold on, don't do it yet. We're going to scroll past this and do number 4 because number 4 tends to be something that's confusing to you guys. And again, I try to do all the different options you'll see on Alex on our notes always. So quickly scroll past 3. We're going to 4. So it says, suppose that the function is defined on the interval, which just means all numbers. So this one's different. We've been used to seeing the x part be inequalities, like less than or greater than symbols, but these ones have equal and not equal ones. These are a little bit different. You don't see these too much, but I do want to go over it in case you get confused on Alex. So what an equal sign actually means here is that y is equal to -4 only at this particular number, only at 0. So not like greater than 0 where it's a whole bunch of numbers, it's just 0. Meaning this is just a point. So whenever you see an equal sign, it's just one point. So the point is 0, and then 0 equals -4. Okay. So again, we like to start these by making your boundary line. Our boundary line is 0, so you make a vertical line at 0. We're going to actually draw the second one first because I think it's a little bit easier to see. So again, we're going to plot our point 0, -4. And a point is a solid circle because it's defined there. It equals that. And then the first equation was y equals +4. So again, a horizontal line at 4. But look at your boundary line. This is going through it, and the blue line's going through it, so we can't have two closed circles because it's not a function. But let's look at our domain. It says if x does not equal 0. So at 0, it doesn't equal this equation. So we have to put an open circle at 0, -4. So you just make this an open circle instead. So it doesn't go through it. That way our boundary line has an open and closed circle on it. And then that would be our final answer. So pause here, go back up to number 3 and try that one all by yourself before we start doing the harder ones, the ones you see most likely on your test. All right, number 3, it's a little bit of a squished one, so bear with me here because the numbers are small. On all of these, they all had solid circles on the left, all had open circles on the right. And again, these are just, I call these like the step problems. These are just steps, just like number 2 was. So just little steps defined. We should get a little bit in the habit of doing those ones, which is going to be now much different than our advanced ones. But like I said, once we start learning the advanced ones, you guys tend to think these are easier than the ones we just did. So you'll see which one you like more. But these are the ones that are definitely on your test, what we're going to test you on. All right, so now you can tell that these are different because now you actually have like equations here where they're not just like nice whole numbers anymore. The nice whole numbers, again, just mean they're horizontal lines and those should be easy. These are now just our normal lines that you guys are used to graphing. So this is y equals x minus 4 and y equals negative 2x plus 2 on these new domains. Okay, but we're going to start off our problem just like we did earlier. So we're going to make our boundary line. Our boundary line is 2 and only at 2 because we only have 2 neighborhoods. We have the left neighborhood and the right neighborhood. And each of these graphs is only going to belong to one of them. All right, so let's do the first one. The first one is y equals x minus 4. And it's going to be on the boundary x is less than or equal to 2. So is that the left boundary or the right boundary? For less than 2, it's going to be the left boundary. So that graph is only going to belong there. If you extend it to the right-hand side, you are going to be marked wrong, and that's where most people make their mistakes. So only belongs in the left one. So I'll show you the way I suggest you doing it. Because we know that particular point on the boundary line, the open and closed circle, is of most important. So we're going to actually use that number to plug into our chart. So I'm going to actually use 2 because it's put here and it's going to matter. So I'm going to put 2 in here. We're just going to plug in 2 into our equation. So 2 minus 4 is negative 2. And that's going to be a solid circle because of the sign. So I just make a little note there. So 2, negative 2, I'm going to plot. And since this is just a linear line, I know how to graph this because I just count the slope, right? The slope here is just up 1 over 1. So up 1 over 1. Oh, but that means I'm going into the next neighborhood. I can't do that. So we can't go to the next neighborhood, but we know instead of going up 1 over 1, I can just go down 1 to the left 1, and that's still a slope of 1, which is fine. And now we just graph in that neighborhood. And that's our first graph. Then we'll draw our second graph. So y equals negative 2x plus 2. On the interval x is greater than 2. So that one's only going to go in this graph and not overlap the red one. And I'll do an XY table again. I'm going to quickly note that this is an open circle one because of the sign. Again, we're going to use the boundary line number as my x input and then plug it into my equation to find my y. So you plug it into, and so negative 2 times 2 plus 2 is negative 2. So let's plot that point. So 2, negative 2, but an open circle. Oh, wait, that already has a solid circle on it. Obviously, a solid circle takes over an open circle. So that point, for example, on Alex would already be there, so you don't need to worry about an open circle. It just takes over it. But just for our drawings here, I'm just going to make an open circle around it. And again, that we're drawing a line, we just look at the slope. The slope here is, the slope here is negative 2. So start at a point, go down 2 over 1, and here is your line. Again, we knew it had to go to the right-hand side because, for example, if you're like, well, do I go up or down? Well, if you went up this way, it's going to the wrong neighborhood. You have to stay in your neighborhood. So that is your final answer. And again, you're looking at your line, your boundary line, to make sure you have an open and closed circle on it. We do, so you erase it and we are done. And then it's going to ask you, is this a continuous function or not continuous? Continuous just means, like, do they touch? Do they ever merge? Is this like a continuous line? So it is a continuous line because they merged together because of this point here. All right, let's do number 2 together. All right, so let's first do our boundary line. Our boundary line happens to be 2 again because of the X part. So you draw a vertical line at 2 because now we have 2 neighborhoods. So each of these graphs are just going to belong into one of them. So let's start with the first one. The first one is y equals -5x plus 3. You decide which neighborhood it's going into. It's going into the less than 2 one, so it's going into this neighborhood. Okay, now let's actually get the points to graph it. So we always use whatever x is defined on the boundary point. So we're going to use 2. This is going to be an open circle. Plug it into my equation, and it's -10 plus 3 is -7. Okay, let's plot that point. 2, -7 with an open circle is right here. All right, so now just for easiness, so for example, I can plug in different points into my X and Y table if you want to, or I just like to use the fact that we know what the slope is, so I just like to count the slope instead. It just seems to be quicker to me. But again, if I want to go down 5 over 1, which is the slope, 3, 4, 5 over 1, then I'm into the right boundary, which is not my neighborhood. Remember, we're going in the left neighborhood. So again, instead of going down 5 over 1, let's go up 5, left 1. And if that confuses you, just make sure that your slope from one point to the other one is still -5. Whichever way you need to think about it backwards, just still make sure your slope is still down 5 over 1. Or, for example, if you wanted to plug in any point that is any of these numbers, anything that's less than 2, into your equation, you definitely could have done that as well and then just plot these 2 points. So lots of different ways to get your second point. I just like to use slope, but whatever you'd like to use. All right, then we do our second one. So our second equation is y equals x minus 4. Make our table. This is going to be a solid circle because of the sign. And this is going to go in the second boundary because its x is greater than or equal to 2. So we're going to pick 2 again because of the boundary line. We plug it in and we're going to get -2. So 2, -2 with a solid circle. And now we look at our slope. Our slope is 1. So we just go up 1 over 1. We don't have to care about the neighborhoods because we're in the correct neighborhood. So, whoops, so we're good. So we just connect these and we're done. And again, we're not overlapping because that means it's not a function. We're staying in our lane. So stay in your own neighborhood. Notice the red one only stays on the left-hand side and the blue one only stays on the right-hand side. And then we check our boundary line. It both has a closed and an open circle on it. So it looks like we're good to go. And so you erase it and you're done. And then you just have the answer. Is this continuous or not continuous? As you can see, it jumps here. So they don't like connect, so it's not continuous. So that's the difference between a continuous and not continuous one. As you can see for number 1, they touched, and number 2, they didn't. So that's just the only difference. So pretty easy question at the end, but they always just ask it. All right, number 3, let's do one more together before I let you do one by yourself. So hopefully you're catching on a little bit. So where's our boundary line here? Our boundary line here is at -1 because of the domain. So you put a little line. Now let's start graphing. So y equals negative x plus 1. We're going to do our x and y chart. We're going to use negative 1 because it's our boundary line. I know this is a closed circle because of the sign. You put this into your equation. So if I plug in negative 1 into my equation, I would get 2. So negative 1, comma 2, solid circle is here. Now to get my second point, I'm going to look at my slope. My slope is negative 1. Okay, but again, if I'm going to go down 1 over 1, I'm in the wrong boundary. It's not the boundary I want. The boundary I want is the less than negative 1, so we need to be in this boundary. I can still have a slope of negative 1. I just have to go the opposite direction. So I'm still at a negative slope in this way, but just think opposite. So my slope is still down 1 over 1. I just had to count in a backwards fashion, just so I can stay in this neighborhood. And again, if that's too confusing, just plug in another point that's any of these points down here, and you will get a second point. That's totally fine. All right, so let's do our second line. So y equals negative 4x minus 3. Again, we're still using negative 1. However, this is an open circle. If I plug in negative 1 into my equations, 4 minus 3, which is positive 1. So negative 1, positive 1 with an open circle is there. And then we're looking at our slope. Our slope is at negative 4. So we go down 4 over 1, which is okay to do because we're now in the right boundary. So 1, 2, 3, 4 over 1. We connect our dots and don't overlap our neighborhoods. And that looks like a really good graph. We erase the boundary line because it has an open and closed circle on it. And then we're going to say that this is a not continuous graph because they don't share a common point. So try number 4 all by yourself, and we are done with piecewise functions. We still have another section, but we're done with the piecewise part of it. All right, I really hope you guys get this. So this is a continuous one, which means if you saw on your table, they both shared negative 2, negative 4 as their common point. One's open, one's closed, but of course a closed would on your graph just take over it. So this should be your final graph. So I really hope you guys got that. Always, like what I'm going to be checking on, for example, your test when you guys do that, is that your slopes are correct. So like the blue one better have an up 3 over 1. And then the left one better have an up 1 over 1. That's really how I check your piecewise functions on your test. So very much pay close attention to your slopes. All right, so hopefully you guys got that. If not, please rewind and watch this again. It's going to take some of you guys a couple times with these notes or come and ask me for help. All right, last thing we're going to learn about is an absolute value equation. This is particularly for your project, but there's also a topic in ALEKS that you guys need to do in this section. We're just going over the very basic absolute value equations. And like I said, this one should be definitely a review of Algebra 1. So an absolute value equation, if you don't remember what that is your V equation. So it's just two rays with a vertex, shared vertex. It's symmetric, so that's going to be nice when we're going to plot points. And it's mainly in this format. And the reason I'm showing you guys that format is because the vertex is really easy to find just based off that formula. Okay, so your vertex is going to be this inside number, but opposite symbol, and then just this outside number. So it's HK. Okay, so for example, I gave you an example below it. if we have this equation, I can automatically, just by staring at it, know my vertex is opposite this number and then just this number. So your vertex is 4, -7, and then you just plot points on the side of it, and we're done. Okay, absolute value equation or graph is much like the parabola, where it's going to open up if the coefficient in front is positive and open down if it's negative. All right, so for number 1, the first thing you should always do is find the vertex. So the vertex is opposite of the inside. There's no number there, so it's 0. And then whatever number's on the outside, -2. So just by staring at the graph, I already know what the vertex is. So I like to make an XY chart. So it's 0, -2. All you have to do is find one number above, one number below. And since we know that this is symmetrical, we're just going to have to evaluate one of the numbers, and then we'll be done. So I'm going to plug in 1. Okay, so it's the absolute value of 1 is obviously 1. So -4 minus 2 is -6, which obviously makes this one -6. So let's plot those 2 points. And these are just rays that you learned in geometry. And that's your absolute value graph. A couple things to note. We know it went down because of this -4. That means it went down, so it's something nice to check your answer. I'll also show you another trick. The -4 is kind of, for these easy problems that we're going to be doing in this class, this is kind of like your slope. So if you look at your graph from your vertex, we went from -2, we went down 4/1 to each side. So that's another little trick you guys can use too if you don't want to use the table. So for number 2, you have to quickly be able to find your vertex. So your vertex is opposite of the inside. So opposite of -3 is 3. And then whatever's on the outside, there's nothing there. So it's 3, 0. So you plot 3, 0. We know this is going to face down, and that's also our slope. So 2 ways you can do this. We can either do 3, 0 and find one number below and above and plug it into our equation. Or we can use a -2 as our slope. So it'd be down 2/1 on each side. Plot these 2 points. And then you're going to have your absolute value equation. And like I said, you guys need to have this on your project anyways, so it's good for you guys to know how to find these equations. So try number 3 all by yourself and then return back for the answer. All right, your graph here, you should have your vertex at 2, 5. And then you could either make a table like I did here, or you can just count the slope, which is down 2/1. And that is all of piecewise functions and absolute values. So please now, and particularly, do your ALEKS topics on this before you do any exit tickets.